MCV4U1, Chapter 1, Session 11. In this lesson, we are working on Section 1.5 of the textbook, Properties of Limits. We know the statement limit of f of x as x approaches a equals L means the value of f of x become closer and closer to the number L as x gets closer and closer to the number a from both sides. And also x is not equal to 1. This means when we are finding the limit of f of x as x approaches a, there is no need to consider x equals a. In fact, f of a need not even be defined. The only thing matters is the behavior of the function near a. Example 1. Find limit of 3x2 plus 4x minus 1 as x approaches 2. As x approaches 2, clearly 3x2 is getting close to 12 and 4x is getting close to 8. Therefore, the given limit is the same as 12 plus 8 minus 1 equals 19. Properties of limits. Limit of k as x approaches a is k for any constant k. Limit of x as x approaches a is a. Limit of f of x plus or minus g of x as x approaches a is limit of f of x as x approaches a plus or minus limit of g of x as x approaches a. When c is a constant, limit of cf of x as x approaches a is c times limit of f of x as x approaches a. Limit of multiplication of two functions as x approaches a is limit of multiplication of limits of the functions as x approaches a. Limit of f of x divided by g of x is limit of f of x as x approaches a divided by limit of g of x as x approaches a, provided that the limit of the denominator is not 0 as x approaches a. Limit of f of x to the power of n as x approaches a is the same as limit of f of x as x approaches a to the power of n when n is a rational number. By putting this together, we can conclude if p at x is a polynomial, limit of p of x as x approaches 0 and p of a are the same. And if we deal with a rational function, p of x divided by q of x as x approaches a, the limit would be p at a over q at a, provided that limit of qx as x approaches a is not 0. Let's do example 1 using properties of limits. Limit of 3x2 plus 4x minus 1 is limit of 3x2 plus limit of 4x minus limit of 1 as x approaches 2. We used property number 3. Limit of 3x2 is 3 times limit of x2. Limit of 4x is 4 times limit of x as x approaches 2. And limit of 1 is 1. By property number 7, limit of x2 as x approaches 2 is limit of x to the power of 2 as x approaches 2. Limit of x as x approaches 2 is 2. Putting all these together, we see the limit of 3x2 plus 4x minus 1 as x approaches 2 is 19. It's a polynomial, and for polynomials, we know limit of f of x as x approaches a and f of a are the same. Evaluate limit of x2 minus 5x plus 2 over 2x3 plus 3x plus 1 as x approaches negative 1. The limit of a quotient is division of limits as x approaches -1. Limit of numerator is 8. Limit of the denominator is -4. You can apply the conclusion of properties or use those properties one by one and find the limit, which is -2. Limit of square root of x2 over x minus 1 as x approaches 5. It is the same as square root of limit of x2 over x minus 1 as x approaches 5. Limit of division is division of limits, and limit of x2 as x approaches 5 is 25. Limit of x minus 1 as x approaches 5 is 4. Therefore, the given limit is square root of 25 over 4, which is 5 over 2. Sometimes limit of f of x as x approaches a cannot be found by direct substitution. This happens when direct substitution results in an indeterminate form 0 over 0. In such a case, we look for a covalent function that agrees with f for all values of x except x equals a. Let's have a couple of examples to understand it. When we try to find limit of x2 minus 2x minus 3 over x minus 3 as x approaches 3, we face 0 over 0 by direct substitution. Function f of x equals x2 minus 2x minus 3 over x minus 3 is the same as x plus 1 when x is not 3. Therefore, the limit of f of x as x approaches 3 when f of x is the given function is the same as limit of x plus 1 as x approaches 3. And this limit is 4. What we did, we factored the numerator. Since x is not 3, we simplified the function. We divided both numerator and denominator by a non-zero expression, which is x minus 3 in this case. Next example, limit of square root of x plus 1 minus 1 over x as x approaches 0. We rationalize and simplify. We rationalize the numerator of the fraction and simplify it. This limit is the same as limit of 1 over square root of x plus 1 as x approaches 0, which is 1 over 2. Let's explain why this limit is 1 over 2. It is direct substitution. But if we want to show our work in a little bit more detail, we say this limit is the same as limit of 1 as x approaches 0 divided by limit of square root of x plus 1 as x approaches 0. Limit of a constant is the same constant, therefore limit of numerator is 1. Limit of square root of x plus 1 is the same as limit of square root of x plus 1 plus limit of 1. And limit of square root of x plus 1 as x approaches 0 is the same as limit of x plus 1 as x approaches 0 to the power of 1 over 2. Property number 7, which is also 1. Let's find limit of x plus 8 to the power of 1 over 3 minus 2 over x. We can rationalize numerator of this fraction by using the fact that cube root of a minus b times cube root of b times cube root of a2 plus cube root of ab plus cube root of b2 equals a minus b. The textbook used another method, said this quotient is indeterminate form. When x is 0, it is 0 over 0. And they assumed u equals x plus 8 to the power of 1 over 3 and found x equals u3 minus a. Therefore, the given limit can be written as limit of u minus 2 over u3 minus 8 as u approaches 2. Notice that when x approaches 0, u approaches 8 to the power of 1 over 3, which is 2. u3 minus 8 is difference of cubes. We factor it. U minus 2 times u2 plus 2u plus 4. We simplify and then evaluate the limit, which is 1 over 12. Let's work on the cases that limit does not exist. Absolute value of x minus 2 over x minus 2 is 1 when x is more than 2, and it's negative 1 when x is less than 2. Notice that absolute value of x minus 2 is the same as x minus 2 when x is more than 2, and it is negative x minus 2 when x is less than 2. The graph of the function is y equals 1 when x is more than 2 and y equals negative 1 when x is less than 2. The right side limit of the given function as x approaches 2 is 1 and the left side is negative 1. Since right and left side limit are not equal, the limit does not exist. Next example, limit of square root of 9 minus x2, x approaches 3 from the left side. This limit is 0. Since x is smaller than 3 and close to 3, 9 minus x2 is positive and 0. Explain why the limit as x approaches 3 from the right side does not exist. When x is greater than 3, the function is undefined. Therefore, the limit of square root of 9 minus x2 as x approaches 3 from the right side does not exist. Since the right and left side limit are not the same, actually the right side limit does not exist, therefore the limit does not exist. We know the graph of square root of 9 minus x2 is a semicircle, radius 3. By looking at the graph, we see the limit as x approaches 3 from left side is 0 and from right side does not exist. Therefore, the limit does not exist as x approaches 3. Let's recap. If f is a polynomial, limit of f of x as x approaches a and f of a are the same. Substituting x equals a into limit of f of x as x approaches a can yield the indeterminate form 0 over 0. In this case, we have to find a function equivalent to the given function when x is not a. And then by substitution, we find the limit. The key points to evaluate a limit algebraically is direct substitution, factoring, rationalizing, checking right and left side limit are equal, and change of variable. To understand the concepts of this section, solve the questions in exercise 1.5, page 45-46. Question number 1. Question number 4, part D and F. Question number 7, part A, C, and F. Question number 8, part A and C. Question number 10, part C. And question number 11. It's useful to work on question number 12, 13, and 14. Thanks for watching.